Can a powerful theorem from functional analysis guarantee that a mathematical model of a physical system yields one and only one definite trajectory? We are examining the mechanics of this guarantee using Erwin Kreyszig's Introductory Functional Analysis with Applications, specifically the derivation found in Chapter 5, pages 314 through 319. Our objective is to transform a standard differential equation, map its geometric boundaries, and apply the Banach theorem to prove a solution exists. Engineers and physicists rely on nonlinear ordinary differential equations to model reality, from heat transfer to complex planetary motion. The difficulty is that most of these equations are impossible to solve using direct integration. When direct math fails, we turn to computers. But if you throw computational power at an equation without knowing if a solution is mathematically possible, the system can output false data or trap itself in infinite processing loops. Before we calculate, we need a theoretical guarantee that a unique solution is actually there to be found. To find that certainty, we must leave the physical world and enter the abstract realm of operator theory. This framework requires a complete metric space where every Cauchy sequence converges and a contraction mapping. This mapping ensures output distances are strictly less than input distances, scaled by alpha less than 1. When met, Banach's theorem guarantees exactly one unique fixed point. We aren't treating this theorem as a geometric curiosity. We are using it as the engine to prove that differential equations have solutions. We start with an initial value problem. X prime equals a function of t and x. To remove the derivative, we integrate both sides from our starting time, t sub 0, to t, yielding an integral equation. The left side becomes x of t. The right side becomes our initial condition, x sub 0, plus the integral of our function. If we isolate this entire right-hand side, we can define it as our integral operator, t. Our problem is now redefined. Instead of searching for a function whose derivative matches a rule, we are looking for a function x that remains unchanged when passed through the operator t. This translation converts a calculus problem into a fixed point problem, allowing us to deploy the full power of Banach's theorem. Picard's existence and uniqueness theorem formalizes this. It relies on two main assumptions. The function must be continuous, and it must satisfy a Lipschitz condition over a specific time interval, beta. Essentially, if a differential equation is well-behaved and its rate of change is bounded, a unique local solution is mathematically certain. Geometrically, we define this within a rectangle, R, centered on our initial coordinates. Since the function is continuous, its rate of change has a maximum value, c. We can visualize this as two lines with slopes of positive and negative c passing through the center. The solution curve is constrained by this geometry. Because its derivative can never exceed c, it cannot escape the region bounded by these diagonal lines. These algebraic limits act as a geometric cage, ensuring the solution remains within a controlled, predictable space. To begin the proof, we must work in a complete space so our approximations have a valid target to converge to. We define our space as the set of continuous functions equipped with the maximum norm. We must prove that the operator maps this space into itself. By restricting our time interval, beta, to be less than b divided by c, we ensure the output stays within our vertical boundaries. Multiplying the maximum slope by the time step confirms the resulting function's distance from the center is always less than the boundary b. This restriction prevents the operator from generating a function that escapes our assigned mathematical domain. Next, we prove the operator is a contraction. Using the Lipschitz constant k, the distance between two outputs is bounded by the product of k, beta, and the distance between the original inputs. This forces a second restriction on our time step. For the mapping to shrink the space, the product of k and beta must be less than 1. By tightening the time interval, we force the operator to reduce the distance between any two guessed functions with every application. With a complete space and a contraction mapping established, Banach's theorem guarantees a unique fixed point. The proof is complete. A unique solution exists. We can see this in action with a test problem. X prime equals 1 plus x squared, starting at 0. We set up the Picard iteration where each new guess is the integral of the previous guess squared. We start with the simplest possible estimate, a flat horizontal line at 0. Passing that initial guess through the operator yields our first iteration, x equals t. A second pass through the operator yields t plus t cubed over 3. These terms align perfectly with the Taylor series expansion for the tangent of t. Banach's theorem confirms the solution's existence and simultaneously establishes the Picard iteration as a valid constructive algorithm. Every cycle pulls the approximation closer to the analytical truth. This iterative logic forms the foundation of modern numerical solvers used in aerospace, structural engineering, and climate modeling. When we simulate heat transfer across a turbine blade or fluid flow in a combustion chamber, the software is operating within these proven constraints. Without the bounds established by the beta interval, these simulations would fail to converge, producing physically impossible data or system crashes. Functional analysis provides the rigorous framework to verify our equations before we trust the simulations that build the physical world.